Here we are. Welcome, everybody, including our web audience, to the first of the fall Astrobiology series. We're very pleased. There'll be about 4 outside speakers and a number of internal speakers throughout the fall quarter. Our first speaker is Rory Barnes. I'm very pleased to introduce him now because it was about, 1990, we won't say exactly when, he came into my office as a young graduate student. At that point, Upsilon Andromedae was the first multiple planet system other than the solar system to be discovered. And Rory was very keen on looking at the stability of such systems and the stability of planetary systems in general. And he's made quite a career of studying the now many, I can't count them, multiple planet systems and what that implies for the generic stability of planetary systems. And very interesting results that most planetary systems are on the very edge of instability. His thesis, however, I drug him into the topic of planet formation, which he found out to be a very hard topic. But he's been working away at that as well. He got his thesis with me. He then went on to be a postdoc at University of Arizona, where he continued his work on stability of planetary systems. And we're very happy to have him back as a postdoc working with the VPL. He'll join us in January. But right now, he's going to talk to us about the habitability of tidally-locked extraterrestrial planets.
All right.
Extrasolar planets.
Thank you very much, Tom. It's obviously a pleasure to be back here, and even more of a pleasure to be coming back in January. I don't know, can everybody see this? I know it looks like from my end, it was kind of
It's a notes button.
Here.
Notes? Better?
Yes.
All right, very good. So, Tom left out a part of the story in that I've recently started working on looking at how tides affect planets. This was quite a new direction for me because I stopped thinking of planets as point masses and started to imagine them as actually being extended bodies, and lo and behold, there's interesting things to learn from that. But today I want to focus specifically on some of these issues that I've learned looking at the habitability of some of these planets that are going to be around, hopefully we're going to find around low-mass stars. Before I get started, I do need to acknowledge my colleagues here. So Rick Greenberg is my boss down in Tucson. He's definitely an expert on tides and planets. He's probably most well known for his work on Europa. Brian Jackson is a graduate student who is working with Rick and I. His last 2 characters down here probably are familiar to some of you. Sean Raymond is, of course, also a member of VPL. He's now at Colorado. And Andrew West is now at MIT. And they've been helping me out trying to understand some of these issues with planets. So, just as a motivation for what this talk is going to be about, or what really my motivation is for this research, is it comes from transiting planets. And that's this little cartoon right here is meant to show is a transit is when a planet crosses in front of the disk of a star. So what happens is that if an astronomer is at his telescope, he's going to measure the brightness of this star over time, and initially the brightness is very constant, but then at some point it dips, and when we see this sort of dip, the inference is that something is blocking the light. Now, it's more complicated than that in practice, but this is one possibility. And when a transit happens, that's a very important event because you can learn a lot more about the planet than you could if you did not see this transit. The transits provide lots of information. They provide not only just the mass, which you can't get from just radial velocity data, which is the standard way that planets are found. Maybe I shouldn't say standard, but the most common way planets are found. But more than that, it also gets you other actual physical properties of the planet, like the radius, the bulk density. You can measure the surface temperature, perhaps, and you can also measure the atmospheric composition of the planet. Before I get started, we're going to get started here. I want to just mention a few things about a few bits of jargon that maybe some of you heard. I'm going to mainly be talking about super-Earths. I don't think there's a canonical definition of super-Earths yet, but it's sort of anything that's sort of more massive than the Earth, but less than 10 Earth masses. And the reason why 10 Earth masses is sort of this limit is because most models of planet formation suggest that when a planet has more than 10 Earth masses of material in it, it's going to start to accrete hydrogen, and it's going to be more like a giant planet, more like Jupiter. And so this is why this is sort of this magic range. It's because anything less than that is going to have maybe a thin atmosphere is going to be more Earth-like. Now, a transit requires a few special things to happen. It requires the correct viewing geometry. Basically, the orbit of the planet could be oriented anywhere in the galaxy, anywhere in space, point towards any point in the galaxy. But it has to line up so that the planet passes right between you and the star. And so there's some small chance that might happen, and it does happen, and we're seeing these planets. And the other thing that you need is you have to block enough of the light from the star. You have to actually be able to observe that dip that I showed in the previous slide. But I think the most interesting thing about the transits from an astrobiological standpoint is that you can actually measure the properties of the atmosphere. And so this cartoon up here at the top is meant to show sort of schematically how this happens, is that the star emits light, some of that light is blocked by the solid part of the planet, and then this atmosphere around here is able to block part of the light, but not all of it. What happens is that the light, when it comes to Earth, we run it through some sort of apparatus, a spectrograph, and we get the spectrum of the planet. And we might notice some parts of the spectrum have been taken out. These chunks that have been taken out correspond to different elements in the atmosphere, and we can actually measure what the composition of these planets might be like. Now, this has been done for some of the planets that we've discovered so far. We've seen some of these molecules, some of these elements so far: water, methane, sodium, and hydrogen. And this is proof of a concept, at least, that we can really do this for smaller mass planets, because right now all we've really been able to do is see these on these giant planets. We have not actually seen a transit of a low mass terrestrial-like planet yet. So we're going to see these planets, but where are we going to see them? Well, we're going to hopefully see them in the habitable zone, and this is a pretty well-known plot point, especially to people in this audience, so I don't need to belabor it too much. But basically, my laser pointer worked. There we go. It's sort of working. Luckily, there's two of them here. I'm going to try this one. On the y-axis is the stellar mass, ranging from what is said definitely below a stellar mass, or below anything that could be considered a star, on up to a pretty large star. And then these letters here correspond to spectral classes. Don't worry about that too much. The point is that I want you to pay attention to what this mass of the star is relative to m0, which is the mass of the sun. These are low mass stars down here. Of course, the sun is at 1, and that's where our solar system is. Then here on the y-axis, the x-axis, is the distance from the star. And this little river of yellow that runs through this plot is called the habitable zone. At least traditionally, that's what it's been called. This is where basically an Earth-like planet would receive about as much light from its host star as the Earth does from the sun. So maybe that's where planets might be habitable. Now, you might also notice there's this line here. Now, this line has been drawn. I should maybe draw this line, this Tidal-Locked radius. This has been drawn on every plot I've ever seen like this, but it's not really been discussed in a whole lot of detail. There has been some. I shouldn't say there's been none, but there has been a little bit of examination on this. But I really want to focus on what does it really mean to be to the left of this Tidal-Locked radius. And I'm not going to get into that just now. We're going to talk about that in a minute. But the point is that in this region here, the planet could be habitable, but it's also affected by tides between the planet and the star. So, as I mentioned, there are some requirements for being able to detect the transit. We have to be able to see enough light blocked. So, for a 10 Earth mass planet that is Earth-like, that is terrestrial-like, these black lines that I've drawn that are horizontal correspond to how much light would be blocked by the planet during transit. It's called the transit depth quite often. And so 1%, 0.5%, and 0.1%. And from the ground, we can sort of mainly see in this sort of range, maybe 0.5% or bigger. Now, we are launching space telescopes that hopefully we'll be able to see smaller. Oh, what's going on up there? I know. Are the viruses attacking? Sorry about that. If only there were refreshments, we could all have a break now. And on these extrasolar planets, there'll be hurricanes. All right. Thank you. So, okay. All right. So, hopefully, we'll be able to see some of these Earth-like planets. These are 10 Earth masses, so this is sort of the most optimistic case. Where we see a planet that's as big as it can be and be terrestrial-like. we might be able to see it sort of in this range, which is below about 0.2, maybe if you're optimistic, 0.3 solar mass. So a pretty small mass star, but nonetheless, sort of below this line right here and down is where we might be able to see a transiting 10 Earth mass planet on this plot. As I said, you also need to be able to see, there has to be a chance that the planet will actually block some of the light of the star. So a bigger planet, you might imagine, has a better chance of blocking the light from the star because it doesn't have to be tilted directly edge on in order to block the light. It can sort of be a grazing sort of eclipse or a grazing transit. And so these lines correspond to the geometric probability of a 10 Earth mass planet blocking the light of the star. And so what this tells us really is that this region surrounded by the red oval, this is our best bet for finding terrestrial-like planets around stars. Finding a 10 Earth mass planet around any star, your best bet is down here in this very low mass region. So this is why we want to talk about these stars today. And I want to talk about tidal rates. Well, actually, I guess I need to say one other thing before I get to tides. The previous slide, this classical definition of the habitable zone, is based on the idea that the planets are on circular orbits. But we see a lot of extrasolar planets that are not on circular orbits. They're on eccentric orbits. And what does that do to the sort of amount of light that that a planet receives over time? Well, it turns out that it doesn't do a whole lot. There's some work that was done, I guess, 6 years ago now by Williams and Pollard that suggested that for planets on eccentric orbits, what really determines the sort of surface temperature on average around one of these planets is the orbit average of the stellar light that it receives. So, yeah, it receives a lot when it comes close to the star, and it receives less when it's far away from the star. But what really determines it is the average. And I should say, I know that not all of you are astronomers like I am. So what I mean by the eccentricity is sort of the elongation of the orbit. So when you have an eccentric orbit, there's a point that passes close to the star, and then it moves farther away and moves farther from the star. And so as you imagine, as you move farther and closer to the star, the amount of light you receive changes. And what this plot is just sort of showing is that despite some of these variations in the amount of light that the planet receives, is that the surface temperature doesn't really change by a whole lot. Now, an eccentricity of 0.4 is pretty large, but we do see eccentricities that are considerably larger, even in excess of 0.9. But this is at least a starting point to suggest that as we look at sort of eccentric planets, then it's really going to be how much light they receive over the entire orbit that's really going to drive their habitability. And so what my colleagues and I did is we just sort of took these two results and sort of slapped them together of where the habitable zone is and this orbit average eccentricity idea, and just determine what the habitable zones might be. And so that's what this plot shows. And I know it's a little busy right here, but let me just say that there's these shadings here correspond to habitable zones that correspond to different amounts of cloud cover. Basically, the original model of casting has been updated a little bit, and basically if you have water clouds, they can reflect some of the light, and that can improve your habitability if you're close to the star because it reflects some of that excessive radiation. If you're far from the star, you can get CO2 clouds, which actually work sort of as a greenhouse. So these different shadings correspond to just different assumptions about the atmosphere of the planet. What I want you to take away, though, is that at larger eccentricity, the semi-major axis of the orbits that are habitable increases. A over here is semi-major axis. I'm sorry, I didn't mention that right at the beginning. So as I get to larger eccentricities, the habitable zone actually moves farther from the star. All right. So where do tides come in? Well, it turns out that when a planet, or in this case, I've taken a sort of a well-known example from our solar system, when a satellite is close to its central body, its shape can get deformed due to the change in the gravitational field across the planet. So in this model, Jupiter here is the central body, and Io goes around in this sort of eccentric orbit. You can see that it's not a circle, and Jupiter is not in the center. So this is supposed to represent the eccentricity. And Io, its shape is deformed more when it's close to Jupiter than when it's far from Jupiter. And what this deformation does is it basically changes the surface of the planet, and it takes energy to do that. And that energy gets transformed into friction as the shape of this actual planet tries to keep flexing back and forth between a lot of elongation and a little bit of elongation, and for any real planet, that drives heat inside the planet. And not only that, it's actually going to take energy from the orbit and transform it into the frictional heat inside the planet. So it's taking orbital energy and transforming it into heat inside the planet. Another way to think about this is in just terms of what does the planet actually see as it's on one of these eccentric orbits and it's going around the star. In this schematic here, this circle sort of represents the equilibrium shape of this planet, and these wings here represent the deformation of the planet. And this little bulge here, this stretching of the planet, always wants to point towards the star. And so when it's on an eccentric orbit, the star seems to move around relative to if you were standing on the surface. And so the bulge tries to follow that the gravitational source of the perturbation, which is the star. And so what this says is that the tide really is going to vary over the course of an orbit. And that's just another way of saying what I just said, that the shape is going to change over time. But in reality, for any sort of real body, this is not going to be just instantaneously caught up to wherever the star is. It's going to lag. It's not going to be able to keep up. It's not going to be able to adjust instantaneously to the position of the star. And so this is going to lead to a torque on the orbit, that there's going to be this asymmetry in the system, that it's not going to be perfectly lined up like it's shown here. And it is this sort of asymmetry that's going to really result in the orbits shrinking and circularizing. So over time, these orbits are going to slowly collapse towards the star, and they're going to go from being very elongated to being circular. So that's really the process of tides, at least in the context that we need to know about today. So I've sort of said a lot of these words here, and it might not be very clear, so I want to show you this movie that I think maybe illustrates the point a little bit better. So what I've done here is I've taken a planet that has an eccentricity initially of 0.84. It's orbiting a 0.2 solar mass star, which is represented by that red dot, which is the hand is in the way. Move that. And so as the time is moving on here, notice that it's moving along in billions of years. This orbit, you can see, is slowly starting to shrink. So the blue lines, these correspond to the boundaries of the habitable zone, at least with the 50% of the surface being covered by clouds. And you can see, I guess I need to finish a little bit here. So this dashed circle here, that corresponded to the semi-major axis of the planet, and the actual orbit was the solid black line. And so you can see that the semi-major axis would decay, and at the same time the orbit was circularizing. So let me play it again because there were some things in there that I wanted to point out. Yep, there it goes. All right, so remember, so the blue lines are the habitable zone boundaries. This dashed black line is the semi-major axis of the orbit. So right now, it's inside the habitable zone, but it's pretty close to the inner edge. And the black line is the orbit which is slowly decaying. The eccentricity is dropping. And so even though this planet started out with a very large eccentricity, our assumption would be that it was initially habitable. But then we can see that after 4.5 gigayears, which of course is not a number I just pulled out of nowhere, the planet became uninhabitable. It actually became too close to the star, and it's probably not going to be in a good position for hosting life. So, just to show it in a little bit more of a mathematical way, those lines do not show up very well, so hopefully you can see them. Let's look at the top panel first. So on the y-axis here is the flux that the planet receives relative to that on the Earth, and the y-axis is gigayears. This is for the planet, the model I just showed you. This solid line here represents the orbit averaged flux that the planet received, and then these two dotted lines, which hopefully you can see, correspond to the amount of light that the planet received at its closest approach to the star and at its farthest approach. And you can see there's definitely quite a disparity by about 2 orders of magnitude. But recall that, or I guess I didn't say this, but the orbital period for this planet is only on the order of about 5 days. So it's really whipping around the star quickly. So even though it's got this huge disparity in the amount of light it receives close to the star and far from it, there's enough thermal inertia in the atmosphere that probably this will still be habitable. But you can see it's quite a range. And as the eccentricity decreases, all these three curves converge until finally, when it's a circular orbit, they're all the same by definition. Another point to make is this on this bottom curve, which is that this is the number of rotations that the planet makes during one orbit. So there's been a lot of discussion in the past that planets that are tidally locked, that are close to their star, are rotating synchronously. there's an important difference between synchronous rotation and being tidally locked. Synchronous rotation means that one point remains below the star at all times. Tidally locked has a more technical definition. It means that there is no transfer of orbital or of angular momentum between the rotational angular momentum of the planet and its orbital angular momentum. Don't worry about the details on that. The point is that as the planet moves from being far away from the star to close to the star, there is a torque on this tidal bulge, and that drives the rotation rate. So initially, when the eccentricity is 0.84, this planet is actually rotating 8 times per orbit. So less than 24 hours is this planet's initially its rotational period, its day. And then slowly over time, it drops back down. Once the orbit is circular, then the orbit is synchronous. The planet's rotation is synchronous. So what happens to a planet that crosses through that habitable zone boundary? This planet, maybe it was habitable, maybe it had life for 4.5 billion years. Does the life die? Or maybe, if I were being an optimistic astrobiologist, I would think maybe somehow the Gaia hypothesis is true, and that maybe somehow, despite this rather harsh environment, there is a chance that life might survive. So it's certainly important to think about this tidal evolution. When we think about these planets, they might actually be sort of a laboratory for understanding if this idea of Gaia is actually true. Maybe these planets, as they cross through that boundary, find a way to survive, and we might see planets that we think are not inhabitable, but in fact they show signs of life because this Gaia principle managed to maintain itself or maintain life on the planet. But I don't know. That's certainly a lot of room for speculation there. But although I sort of throw this out as a hypothetical, we're actually kind of getting close to actually being able to see planets that might be doing this. There's a system that was discovered about a year ago called Gliese 581. It got a lot of press. It actually was the headline on CNN.com for a few hours, but that was in the middle of the night. So anyway, there were 3 planets in this system. This inner one is quite large, but then there's 2 that are, at least their masses could be as small as 5 Earth masses and 8 Earth masses. So they're in that magic super-Earth range. But what's really interesting is that this middle planet is just interior to the habitable zone. Well, or maybe it even is in the habitable zone, if I was really optimistic about its cloud cover. All right. So this is the 100% cloud cover boundary. This is 50%, and this is 0. By the way, the Earth's cloud cover is somewhere around 40%. So that's why I sort of think of 50% as sort of the magic boundary here. So the question that my colleagues and I asked ourselves, well, could it be that Gliese 581c was in the habitable zone in the past? In other words, is it one of these kinds of interesting planets that might be able to test the Gaia hypothesis? And so what we did is we considered several different models of the planet. Now, I don't want to go into this in too much detail, but you can imagine that the planet might have different compositions, and so it might have different properties, and I sort of just summarize their properties in terms of radii. The composition, as you might imagine, can determine what the radius of the planet is. So for several different radii, we plotted what would the semi-major axis do relative to the habitable zone boundaries back in time. So basically, we just take our tidal model and rewind it, and just to try and determine, could the planet have been habitable, or at least more habitable in the past? And so, these shadings represent those same sorts of planetary conditions that increase or decrease the chance of habitability. And so for these different models, you can see, well, for the smallest mass planet, maybe 10 gigayears ago, this planet was inside the habitable zone. I'll just call this 50% region the habitable zone from now on. If it was bigger, it could have been in the habitable zone more recently, and if it was really big, it could have been it could have almost reached the sort of very most conservative definition of habitability, not requiring any cloud cover. It wouldn't have, but it would have gotten close about 10 gigayears ago. And we don't really know the age of the star very well. There's actually quite a bit of controversy over that. It could go anywhere from about 4 billion years to 10 billion years. But nonetheless, this is sort of suggesting that these kinds of planets could be out there. The reason why I can't say definitively that this planet is in the habitable zone is because there are other planets in this system that provide important constraints. As Tom was mentioning, I've done a lot of work looking at the dynamics of multiple planet systems, and so I can assure you that these planets would go unstable if I were to follow these tracks. And of course, what I mean by unstable is that the planetary system would actually break apart due to its gravitational interactions between the planets themselves. So, given that we see a planet today here, that means that it couldn't have been destroyed earlier. So it's a rather simple argument, but the point is that even though in this case we can't say that this planet maybe was some sort of fossil planet where there was life, and it's now there may or may not have life, we're getting sensitive to these kinds of planets, where we could actually make these kinds of assessments as to whether or not these planets were in the habitable zone, and maybe we can start to understand, how robust is life to these sorts of changing environmental conditions. All right, now I need to shift gears again. I want to go back to tidal heating. I mentioned that very briefly in the beginning. So just to remind you, recall that as the planet goes around in its orbit, on an eccentric orbit, the shape is changing and it's getting heated due to this working of this planetary shape. And this, of course, has dramatic consequences in our solar system. I hope all of you have seen this wonderful movie of a volcano called Tvashtar on Io. It was taken by the New Horizons spacecraft on its way to Pluto about a year ago. This is this volcanic plume that was visible at the time of the flyby by Jupiter, and it's obviously a huge volcano relative to the size of the planet, and this volcanism here is driven completely by tides. So it is this. There is no other source of energy that is driving this, or at least very little bit of any other energy on Io that could be driving this. And so the orbit change is accompanied by this internal heating. And so what we next asked ourselves was, could tides, drive volcanism on exoplanets? And so we're going to use the same tidal model I've been talking about. I didn't go into any detail, but I want to make this point very emphatically that the model that we're using to sort of understand tides on these exoplanets was actually used to predict volcanoes just like this on Io. So, before Voyager got to Jupiter, Stan Peel and collaborators said there's going to be volcanism on Io due to tidal heating, and it's going to be huge. And literally like 3 days later, after the article came out in Nature, they discovered this from the Voyager spacecraft. And this was independent of any knowledge of the composition of Io. It was just assuming that this had to be a body that was made of standard stuff. It had to be kind of like rocky material, and we were going to see volcanism. And so as we think about these exoplanets whose compositions are completely unknown, realize that this gravitational effect of tides will probably trump the compositional variations that you might be worried about. So what we did is we basically took planets in these habitable zones that I described where we do incorporate the eccentricity. And we said, well, what is the tidal heating that these planets receive? So these planets are going to be right smack dab in the middle of the habitable zone around low mass stars. And so what I've plotted here is this heating flux. This is sort of the standard way to measure the amount of internal energy coming out of a planet. It's basically the energy coming out through unit surface area on the planet's surface. And what we looked at was we just said, okay, suppose a planet is sitting right in one orbit, right in this orbit. It's not evolving or anything like that. We're just going to observe it. And this region right here would correspond to planets, 10 Earth mass planets, that have heating rates larger than Io. Io's heating flux is 2 watts per square meter. That's this contour line right here. So this dark shaded region, if I found a 10 Earth mass planet orbiting a 0.15 solar mass star with a large eccentricity, it's going to be an Io-like planet. I don't think there's really much way around it. And you can see, in fact, that the heating rates can be orders of magnitude larger than Io, 10 or more. So, and this is just right in the middle of the habitable zone. It turns out that the tidal heating is very sensitive to the distance that the planet is from the star. It actually goes as the distance to the 6.5 power. So that just means if I move something by 10%, the heating rate is going to double. So as I get closer into the star, the heating rate goes up dramatically. And so if I find a planet near the inner edge of the habitable zone, it's almost assuredly going to have these monster heating fluxes. And as, of course, a planet that orbits closer to the star is even more detectable. So what I think this is telling us is that maybe that the first planets that we really see, that we really spot in the habitable zone or even maybe interior that are terrestrial-like, they're not going to be Earth-like planets the way we like to think about them. They're going to be super Ios. But heating isn't all bad. On the Earth, heating can do lots of good for us. It drives the plate tectonics, which drives the carbonate-silicate cycle. This is not my area of expertise, but let me try and explain it. I'm sure a lot of you have seen this before, and I stole this image from Jim Casting's website. So it's pretty well documented. But the basic idea is that when you have plate tectonics, you're able to keep carbon dioxide out of the atmosphere, and carbon dioxide is a greenhouse gas, and so the plate tectonics prevents Earth from becoming a Venus-like planet, which would be bad. So what happens is that if it's a cycle, so I can kind of start anywhere. If volcanoes emit carbon dioxide as they erupt, carbon dioxide goes into the atmosphere, then storms happen. The carbon dioxide interacts with the continents through weathering, and the carbon dioxide is brought into the ocean where it reacts with the water in this environment, and it precipitates out and becomes part of the oceanic crust, and it's then subducted down into the mantle, and then it erupts again. So the way I like to think about it, just as an astronomer, is that this is just a little game for carbon dioxide to play, rather than building up in our atmosphere and having a big party with all of its carbon dioxide friends. So the point is just that when we can get something for carbon dioxide to do, it's not going to cause a planet to become uninhabitable. So we don't really understand plate tectonics, even on the Earth. But one thing we do know, a sufficient but not necessary condition, is that there has to be an internal heat source for heating to drive plate tectonics. So it may be that tidal heating could do that. It may be that tidal heating can't do it, but it may be that it could. We don't know the answer yet. But if I have tidal heating in the right kind of range, maybe we can drive plate tectonics and improve a planet's chance of being habitable. And so this is that same plot I showed you before, but now this lighter shade, this corresponds to a limit that maybe can drive plate tectonics. And so here, before we had said this is going to be an Io-like planet. That's probably not good for habitability. But if I have less heating than Io, but enough to drive plate tectonics, the limit is thought to be about 0.04 watts per square meter, then maybe this is a nice, happy region for planets to support life. This white region out here, this is basically where the heating rate is too low for plate tectonics, but there could be other sources there still. There could still be radiogenic heating. That's what drives plate tectonics on the Earth. We certainly can't rule that out on these exoplanets. In fact, it may even be very likely that there's going to be this radiogenic source. We just don't know. It's not very easy it won't be easy to measure that. But the point is in here, we certainly will know, just based on the mass and the orbits of these planets, that there is some sort of engine inside this planet that could possibly stabilize the climate over long terms. So this might suggest that there's sort of a geophysical habitable zone, that there is sort of a sweet spot where the tidal heating can make the planet habitable, or at least encourage it to be habitable. We certainly don't want anything to be like Io, where there's too much, or too little like Mars, which it went dead. But it may be that when you have sort of just the right mixture, it becomes just right. And so this suggests that there's another way to think about planetary habitability, that it's not just the classical habitable zone definition that Casting suggested, that in fact there is sort of a geophysical habitable zone as well that overlaps with it. And so here, this is basically just my own version of the Casting cartoon that I showed you earlier with the yellow strip of habitability. That's represented by these black curves. And then these red curves here, these correspond to these tidal heating limits of 2 watts per square meter and 0.04 watts per square meter. And so it suggests then that where these two regions overlap, this is really what we mean by a habitable zone around low mass stars. That between these red curves and black curves in this region right here, this is where we would want to look for a planet, of course with an eccentricity of 0.5. So I would argue that if we're going to try and look for these planets around low mass stars, this is really the preferred region to hope to find a planet, is somewhere in between these two curves. Now, and again, I should mention that these red curves are again for a 10 Earth mass planet. Now, the eccentricity matters, as I said before. When your planet is more eccentric, the heating rate is going to be larger. So I'm going to have another movie here, and I'm going to show you just how these habitable zone boundaries change with time. Or not with time. That was exactly what I wanted you not to think. It's not time. Its eccentricity is changing. And so I'll play this a few times. So as the eccentricity of the planet is changed, if I suppose I just think about finding different planets with different eccentricities, this is how the habitable zone boundaries will change. So you can see that initially, as eccentricity goes up, here, let's see. As eccentricity starts to increase, the sort of the geophysical habitable zone changes quickly, and it's not until I get to large values that it stops. Why did it stop at 0.86? I don't know. Well, but once I get to large eccentricities, then the sort of the classical zone changes too. What I think is almost the most remarkable thing about this plot is that the two boundaries overlap for so much. You know, these are two totally different processes, and yet for a large stretch or for a large fraction of this parameter space, you know, the habitable zone boundaries the habitable zone is, they overlap. The two regions overlap. So that might be interesting. But of course, as a famous politician once said, it's not all about just where you find the planet today. It's what had happened in the past. The past matters for these planets. All right. So I want to play another movie for you now, and this is what happened to a planet in the past. Suppose we discover a planet at this blue dot right here. This would be a planet around a 0.15 solar mass star. It's 10 Earth masses. Its semi-major axis is 0.05, and its eccentricity is 0.03. I think most people who study extrasolar planets think that this is a pretty good bet for at least a planet analogous to this will be the first kind of planet that we're going to detect through transits around these other stars, these small mass stars. And notice that I've even made it even more tightly of a constraint here, and that I've now stuck it in the middle of this astrogeophysical habitable zone that I've just defined. So this is really would seem to be like an ideal case for what we might consider to be a habitable super-Earth. But if I rewind the tides now, if I just say, okay, what happened in the past to this planet? So as I'm going backwards in time, so this clock is counting backwards in time, and watch, I'm counting the heating flux here. The eccentricity is growing, and then just about 3 gigayears ago, it was actually at this Io limit, and it's not going to stop. It's just going to keep going. And so, of course, it depends on how old this planet is, but in the past, the heating rates could have been quite a bit larger. This is going to get all the way up to about 15. So about a factor of 10 more volcanism, more outgassing, more heating than on Io. There's a critical difference between a 10 Earth mass planet and Io, though, and that is that a 10 Earth mass planet can hold on to its atmosphere. Io is 1% the mass of the Earth. It just loses its atmosphere almost immediately. So if a super Earth like this had heating more than Io for 7 gigayears, it very well could be that this planet's atmosphere is dominated by what could be, let's see if I can get it to go again, what could be a lot of bad stuff. A lot of, it could be dominated by carbon dioxide. It could have a lot of sulfur dioxide. It could have become uninhabitable and remain uninhabitable even as it enters into the habitable zone down here. So even though we see it in the habitable zone, even in this more tight definition of a habitable zone that I've just described, it still certainly does not mean that that planet could be habitable. So it's past that critical point, so I'm going to move on here. So see if maybe I'll move on. How about there? All right. So I would argue that planet could very well be more correctly considered a super Venus, where the early planet, or early in its history, the planet had quite a large amount of eruptions. It turns out that the sulfur dioxide that is typical on eruptions in our solar system is not very stable in atmospheres. It can either be photolyzed or it could precipitate out with water if there's any water left in the atmosphere. And so you could just end up with sort of a 10 Earth mass super Venus, just a planet that has an absolutely massive envelope of carbon dioxide or perhaps other outgassed material, and that might be a typical kind of planet we might see around these low mass stars. Of course, as I said, super Ios, I mentioned those before. So it might be that if I don't see just all this carbon dioxide, you might still be able to see a lot of the current. If you saw sulfur dioxide in the atmosphere, that would be maybe indicative of there still being a lot of volcanism on the planet. And so, of course, as I said, the planet would have its atmosphere. So this might be more like what you'd see. And I know the graphics are amazing, but the point is nonetheless that, there could be these sort of, if you could see planets that had a lot of sulfur dioxide and carbon dioxide in their atmosphere, they might actually suggest that they are super Ios going on under there, that they are, in fact, have a lot of volcanism going on. There's another possibility that's pretty interesting, and that is that maybe these are going to be kind of super Europa-like planets. It's well known, and I haven't talked about this at all yet, but M stars are very active. They tend to blast off a lot of material from their surfaces, and these ejections can basically strip off an atmosphere right away. Just one of these ejections could possibly do that. And a lot of times people have thought this is going to be bad for habitability, that a planet needs to have an atmosphere. Well, instead, if you think about it in this new context, well, then perhaps they don't need an atmosphere. Maybe this is actually the most favorable kind of condition for life, where I have an internal heat source that's going to melt a water surface. Let me back up here. I was getting ahead of myself. So imagine a planet that has a large amount of water on its surface. Initially, if that planet has an atmosphere, that water is going to be in liquid form. But once the atmosphere is stripped away, then the surface temperature is going to drop quickly, and the planet might become iced over. And that is going to be that's basically like Europa, the moon of Jupiter. And as I mentioned, my boss Rick is big on Europa. He's done a lot of work on that, and I know that some of the work is controversial, but the point here is that there could be sort of this boundary layer of ice on a planet where as the planet moves around in its orbit, it gets deformed and the ice is brittle just like it is on Earth, and it's going to crack, and you might end up with little seams in the icy surface of this planet where organisms can move around. And because of there's tidal heating underneath in the core, then you're going to be able to melt the ice that's below the surface. You're going to have sort of a water mantle. You have kind of energy. Maybe you're going to have black smokers and things like that. And moreover, is that this M star that's very active is going to drop a lot of high energy particles on the surface, and they can interact through surface chemistry and create they can create molecules that could be beneficial for life. So, in fact, the whole problem with the atmospheres of these planets was you might lose them, but you could sort of think of this sort of ice region as sort of a very thick atmosphere. That's going to be really good to protect you from a lot of the radiation from the star, and in fact, the radiation might even help you. So, a super Europa, or maybe it doesn't even need to be a super Europa. It could be a small Europa. That might help a lot too. Another possibility is that you could imagine a planet that had a lot of volcanism, and you might think that would build up in the atmosphere, but instead what happens is that the activity from the star keeps blasting off some of the atmosphere. So you might imagine that as this volcanism is coming out, it goes into the atmosphere, and then all this radiation or activity from the star is going to blast off parts of the atmosphere. This is obviously a delicate balance, but it could be something else we could imagine, is that it might be that these planets keep replenishing their atmosphere even though the star keeps trying to blast it off. So I've just sort of talked a lot about all these gravitational effects, but I've left out composition. And although I said not too long ago that we can expect the tides to dominate the composition, or to be more important than the composition when it comes to imagining the volcanism and the heating rates, we do know that for sure the composition matters. We need to have water on these planets. They need to be able to have the right resources for life to develop. Well, it turns out that there's been some work that was done by Vicky and others that suggests that it may be that these planets around these M stars are going to be pretty volatile core. In this simulation, basically they started with planetesimals, with protoplanets that had a composition that was determined by their local origin. So in each of these panels, the left panel here, the y-axis, is the eccentricity. That's not so important in this context. But this x-axis here corresponds to the distance that each of these little bodies is from the star initially. When you're close to the star, which is on the left here, the composition tends to be volatile core. That's because it's close to the star and there's too much energy from the star to let the volatiles form. But farther away, they can be water rich. And so these colors correspond to the amount of water basically on each of these bodies. So red is dry, blue is very water rich, and the Earth is somewhere in sort of this yellowish green area. And so around not a very low mass star, about half a solar mass, the simulation goes on. All these bodies kind of interact with each other. They hit each other, and basically over time, this what was initially a very discretized sort of composition of this disk gets all mixed up because these bodies, these blue and red bodies are intermingling, but they don't intermingle enough that essentially at the end of the simulation, when you just have a few bodies that would be a solar system, a regular planetary system, they would be pretty dry. Yeah?
What happens to smaller stars?
Yeah, that's the next point, is that it gets worse. As the star gets smaller, this problem only gets worse. So this suggests that, well, it's all great that I spent all this time talking about habitable planets, but we're not going to have them. But I knew that was not going to be true, because Sean has also done some other interesting work where it showed that it's possible that you could form planets in a different way. The previous way, I think, is the way most of us sort of imagine planets forming. They just sort of form from their local stuff. But it's possible that you could have planets moving around inside this disk of forming planets, and these planets can push material around in ways that you maybe didn't expect. So this is a very similar kind of idea, where now I'm taking a one solar mass star and I slap down a disk of rocky bodies, again dry in here, some water, lots of water, and now I've stuck Jupiter out at the end. Now, what's going to happen in this movie is that what you don't see is that there's a lot of gas in this disk still, and the gas can actually push Jupiter around. And so in this movie, what happens is that Jupiter is migrating in. This is actually becoming a pretty well-known phenomenon in astrophysics, is that these planets are going to migrate around. And in this case, what happened is that Jupiter actually moved in and pushed a lot of this water-rich material into this inner region. And basically, you get left with planets that have a lot more blue in them, which is good. So this might be a way in which we can form these planets to be volatile rich. But there's a problem in that, let's try that way. When you have multiple planet systems, things get a lot more complicated. Basically, these orbits can change over time because the gravitational interactions between the planets can drive eccentricity oscillations. So these orbits go from being circular to stretched to circular to stretched over time, and this can lead to things like variable internal heating rates, variable stellar flux, and variable rotation rates over time. So as an example, I want to mention, suppose I go back to the system Gliese 581, and now I want to stick a Jupiter-mass planet on the outside of these other three planets at 0.75 AU with an eccentricity of 0.3. This eccentricity is about the mean of the known extrasolar planets. And so just remember that planet C is interior to the habitable zone and D is exterior to the habitable zone. And I'm going to show you this movie. Oh, that started going. Where this shows sort of how all these different interactions occur. So in the top panel here, these are the orbits. So blue is the outer planet, D, and C is the middle planet, red. It's red. I don't show the other two planets that are in the system. And you can see that they oscillate around the star, which is this fixed black point here. And as they oscillate around and the orbits become elongated and less elongated, the heating fluxes and the stellar light that they receive change over time. So down here, this is the logarithm of the heating flux, and these blue dots are just the values that they have at any moment. This is the Earth, and this is Io's values, and you can see that they move back and forth over time. This is the stellar flux down here on this bottom bar. This dot here at the center corresponds to the orbit average flux, and then so as the bars grow and shrink, that corresponds to the the close approach amount of flux it receives and the far approach, the farthest distance amount of flux. So over one orbit, so and we'll be here for the moment. This is how much starlight the planet received on average, but then it also receives this amount at any particular moment. So let's play that again. So you can sort of watch, if you kind of pay attention, when the red dot gets up to Io, look up here real quick and you'll see that it looks a little more elongated. And then as it comes back down here, look up and you'll see it looks a little more circular. And so there's this complex interplay then, where if I expect a planet to have the right ingredients for life, it's also going to be going through all these oscillations. And note that these timescales are not very long. These are just, especially in terms of the atmosphere, these are going to be forcings that are going to really change the properties of these planets quite quickly. So let's see if I can move on here. I think I'm running a little late on time here. So one way to think about this is that these panels or bars just correspond to different kinds of physics. There's the astrophysics of just how the orbits are going to change. There's the geophysics of how the interiors of these planets change, and then there's also the atmospheric response to how the flux changes over time. And so you can imagine that as we think about where these planets are going to be, we can sort of imagine a parameter space where we might expect to see different types of planets appear. And just for fun, really, I just labeled these different parameters for visualization as astrophysics, geophysics, and atmospheric science. And what we might expect then is that we really need to understand where these planets, what types of planets are going to live in which parts of this parameter space. I hope that the plural of Venus is V9, but I don't know if it is or not. If it hasn't been decided yet, that's what I argue for. It should be V9. But the point here is that there's going to be a lot of different complex phenomena going on here, but yet somehow we could expect that super IOs all share a certain kind of common properties, and it's the same with all of these. And so what we need to do is understand how to actually pick apart all the different physics here and understand which planets are likely to be super Earths versus which ones are likely to be super Venus. So what we really need to do is somehow go from this kind of image of where we see a black dot in front of a star, which we know is a transit, and then understand, well, is that black dot really a super Earth, a super Europa, a super Venus, or a super Io, or any other kind of planet you might want to imagine? And that's really what the task is, because these planets are going to be found. And moreover, we actually have a tool that's coming online here very soon that hopefully will be able to measure some of these properties, and that's the James Webb Space Telescope, which will actually hopefully be able to measure some of these molecules in the atmospheres. Of course, the super Europa doesn't really have an atmosphere, but maybe if we point James Webb at one of these planets and we see nothing in its spectrum, maybe that actually means it's a good bet for being habitable. Maybe it's one of these ice worlds. So hopefully, in 5 years from now, once we can actually do these sorts of detections, we'll have been able to build up this theory well enough to understand when we look at how we want to, first of all, divvy up the time on the James Webb Space Telescope to actually spot super Earth, which is, of course, the grand prize. But maybe we'll also be able to distinguish between these other possibilities. So let me show you my summary slide here. So I hope that I've convinced you that the gravity is important for these kinds of planets around low-mass stars. That it's really going to drive a lot of the properties of these planets. That I made this point early on, that the tides can actually pull a planet out of or into a habitable zone. I didn't really talk about into, but that's going to be much less of an effect. As I said, the power of tides falls off very quickly with distance, so it's unlikely to pull a planet into the habitable zone. The tides can dominate over planetary heating. I guess I forgot to mention that the heating rate on the Earth is about 0.1 watts per square meter. So when we're talking about IOs and super IOs, those are orders of magnitude more heating. The tides can set the planetary rotation rate, not just synchronous. They can actually drive rotation rates that are faster than the orbital period. As I said before, also the orbit average flux apparently determines the surface temperature. So as we see eccentric planets, we need to bear in mind that the eccentricity can matter as far as just how much flux the planet receives over time. There's a whole wide menagerie of possibilities for what these planets can be. Obviously, when you start thinking about tidal heating, surface fluxes, rotation rates, and then they can change over time, I think the sky is the limit as to what kinds of planets you can imagine. And so it'll be interesting to try and figure out how to distinguish all these different possibilities and really understand which kind of planet is habitable. But I think, moreover, I sort of suggested a refinement of the habitable zone where we also consider the internal heating in addition to the stellar flux. I think that I would argue that habitable planets are most likely to be in multiple planet systems, which just is, again, drives all this complexity and leads to things like variable rotation and rates and heating fluxes and just stellar flux. And so somehow what I'm hoping to do when I come here in January is work with Vicki and try and put all this together, obviously with a lot of help, and hopefully we'll make some progress towards being able to determine whether these planets are going to be habitable or not. So that I'll stop. Thanks.
Thank you, Rory. Do people have questions?
Yeah.
I'm wondering what effect your simulations would show if your planet had a large moon like the Earth does. Is that able to mitigate some of these astrophysical effects?
Yeah, so actually there is no chance of that actually being the case. what happens is when you have these sort of tidal effects going on, the moon would actually be ripped off of the planet by the same tidal forces, or it would slam into the planet. There's actually some papers that were done about 7 years ago or so that really showed that these planets will just, their orbits, the moons of these planets would just get stretched out and they would be either stripped off or they would fly to the planet. Though, fortunately, that can't mitigate any of these effects.
Yeah, so in your plots of tidal heating versus eccentricity, above an eccentricity of 0.5 or so, the tidal heating actually goes down.
Ah, yes. That is because the habitable zone moves out. So if you recall, I showed that for large eccentricity, the semi-major axes that correspond to habitable zones are farther away from the star. And so for those, I had put the planets right in the middle of the habitable zone. So above 0.5, the habitable zone is moving out, and so that's what's making the heating rate less. So yeah, that is a subtlety of those plots. That yeah, I should have mentioned that. So.
Nick?
So the importance of the tidal heating is going to depend on how many of these terrestrial planets are, at least start off on eccentric orbits. Do you have a feeling about that given the sort of formation and migration scenarios like planet-planet scattering versus gradual migration or something?
Yeah, so migration rates tend to not drive eccentricities up really large. Sort of, maybe 0.1, 0.2, at most 0.3 is the largest eccentricity that migration can tend to produce. Scattering can eject planets, so eccentricity is larger than 1. And it seems that a lot of people have done simulations, and it sort of suggests that they can fill in that whole range from circular to basically just barely on the edge of not being ejected. So I think there's basically a sort of a peak at around 0.3, but I think that's pretty broad. Sort of anywhere from 0.1 to 0.5 is going to be typical. So, and from the known exoplanets that we see, the peak of eccentricity is about 0.3. So it's not going to be. Assuming that exoplanets form in similar ways as terrestrial exoplanets form in a similar way as the gas giants or the giant kinds of terrestrial exoplanets, they're going to be sort of with similar orbits, I would imagine. But I don't know.
Any other questions? Suzanne?
Do your simulations show anything about how our own solar system formed? I mean, I guess what you're saying is that like the Earth couldn't have formed today and then pushed out
Yeah, well, I didn't really look in our solar system very much. For our solar system, the tides fall off very quickly as well. I mean, you might have noticed in some of those slides I showed that Mercury has been affected by tides. It's in this, its rotation rate is set by tides, but the tides don't come out as far as the Earth. So this really doesn't affect the picture of formation in our solar system very much.
You think that the Earth probably formed in a fairly circular orbit, eccentric?
Well, I suppose it just depends what you mean by circular or eccentric. I mean, the Earth's orbit is not circular right now. Certainly, as it was forming, it was getting jostled around. I mean, it certainly had to go through phases where the eccentricity was larger than it is now. But I mean, I would say maybe 0.1 is sort of probably the eccentricity that the Earth got in its forming. But again, I think it's such a stochastic process. All this, being hit by lunar-sized objects or Mars-sized objects that form the moon and things like that. That I can't really speak to how large the eccentricity there ever got. But I think most simulations sort of suggest that terrestrial planets tend to not get eccentricities over about 0.1 or 0.2 as they form.
More questions? Any questions from the web? No? Okay, well then let's thank Rory once again.
Thank you very much.
For a great talk.